Welcome back to QHSE Talks. You know, the most dangerous piece of equipment in your office right now isn't the heavy machinery down the hall.
Right, it's really not.
And it isn't the electrical panel in the utility closet either. It is actually the squishy, contoured foam inside the chair you're sitting on right this second.
It's true. I mean, we are biologically wired to fear the obvious threats, right? The chemical spills, the sparks, the heights. But the hazards that permanently disable the most workers globally, they don't come with a flashing red light.
Yeah, they come disguised as comfort or as a repetitive routine that feels completely harmless on day one.
Exactly. And then 5 years down the line, a worker can't pick up their own child because their L5-S1 spinal disc has essentially given up. It's just an invisible, quiet crisis.
We are talking about cumulative trauma, and we know exactly why you are here with us today. You are studying for the ASP, the Associate Safety Professional exam.
Yep, and it is a beast of an exam.
It really is. You need to master some incredibly specific, highly technical domains to pass. But more than that, you need the tactical knowledge to actually excel as a safety professional out in the field.
Right. You want to be effective, not just certified.
Exactly. So today, we're placing a massive magnifying glass on a single requirement. We are going to understand the elements of an ergonomics program to just comprehensively break down the science of work.
I love this focus because this isn't just about, memorizing a checklist for a multiple choice test. It's about fundamentally understanding the biomechanics and the systems engineering required to design work so that human beings aren't physically broken by the end of their shifts.
Right.
You are going to be expected to walk onto a floor, analyze a process that looks completely normal to an untrained eye, and identify exactly how that process is slowly destroying a worker's joints.
Okay, let's unpack this, because to do that, to actually spot these invisible hazards, we have to start with the foundational philosophy. We need to define what we're actually doing here. Let's look at the International Ergonomics Association, or the IEA framework.
Yeah, let's start with the word itself.
Right. Ergonomics has Greek roots, ergon meaning work, and nomos meaning laws. So the laws of work or the science of work. But the IEA defines it as a systems-oriented discipline.
And that phrase, systems-oriented, that is the critical distinction you need for your exam. The IEA states that ergonomics is the scientific discipline concerned with understanding interactions among humans and other elements of a system.
Okay.
It applies theory, principles, data, and methods to design in order to optimize human well-being and overall system performance. It promotes a holistic approach.
Hold on, though. When you say holistic and systems-oriented, that starts to sound incredibly broad. I mean, the definition explicitly includes cognitive, social, organizational, and environmental factors right alongside the physical ones.
It does. It encompasses the entire human experience of the work.
But if we are analyzing cognitive load and the social structures of a team, aren't we stepping heavily into human resources territory? Like, why is a safety professional managing how stressed a team is about their production deadlines?
That is a very common point of confusion, and it's vital to clarify for the ASP. We aren't doing HR's job. We are looking at those organizational and cognitive factors because they directly manifest as physical hazards.
Wait, how does an organizational factor become a physical hazard?
Okay, let's say an organizational factor, like a poorly designed piece rate compensation system, incentivizes a worker to move twice as fast as the machinery safely allows.
Oh, I see.
Right. That organizational pressure leads directly to the worker bypassing a safety guard or maybe ignoring the onset of fatigue.
So the psychological stress converts into a physical action that actually causes harm.
Precisely. High cognitive load, like monitoring 6 complex digital readouts simultaneously, it causes mental fatigue. Mental fatigue reduces situational awareness and physical reaction times.
Wow, so their brain is just too tired to move their hand out of the way.
Exactly. Furthermore, psychological stress literally increases baseline muscle tension. If a worker is stressed, their trapezius muscles are tight before they even pick up a tool.
Just from the stress of the environment.
Yes, and that pre-tension significantly lowers the threshold for a musculoskeletal tear when they finally do exert force. You simply cannot separate the cognitive environment from the physical body.
That makes the golden rule of ergonomics make a lot more sense.
The adaptation rule.
Yeah, the rule is the job should be adapted to the person rather than forcing the person to fit the job. Because for centuries, going back to the Industrial Revolution, we built factories and machines, and then we just wedged human beings into whatever leftover space was available to pull the levers.
We demanded the human adapt.
Right. And that expectation of human adaptation is exactly what safety professionals have to dismantle.
The human body has fixed mechanical limits. You cannot tell a worker's spine to simply adapt to a biologically impossible load. You must design the machine, the schedule, the interface, and the ambient environment to fit the natural limitations of the worker.
Which perfectly highlights the difference between proactive and reactive safety. I mean, reactive ergonomics is just waiting for someone's wrist to give out, diagnosing them with carpal tunnel syndrome, and then slapping a Velcro brace on them.
You are just managing the decay at that point.
Right. It's like trying to shave down a square peg to fit a round hole, whereas proactive ergonomics is simply building a square hole in the first place.
Exactly. Reactive ergonomics is a failure of safety management. You are only intervening after the tissue damage is permanent. What you will be tested on and what you must implement is proactive ergonomics.
Meaning you fix it before the injury happens.
Yes. It emphasizes preventing work-related musculoskeletal disorders, or MSDs, by recognizing and mitigating risk factors during the planning and design stages.
Intervening before the concrete is even poured?
Yes. And what's fascinating here is how this transforms your role. You aren't just a compliance cop walking the floor with a clipboard. You become a design consultant.
Oh, that's a cool way to look at it.
This is why we have certified professionals like a CPE, a certified professional ergonomist, or a CHFP, a certified human factors professional. They sit at the table with the architects, the process planners, and procurement managers.
Because they have to speak up during the design phase?
Right. If an architect draws a valve that requires a worker to extend their arms above their shoulders 50 times a day, the proactive ergonomist flags that on the blueprint. They explain that within 3 years, that specific design will result in a 40% increase in shoulder impingement claims.
So they design the hazard out of existence before the facility is even built.
That is the ultimate goal, elimination at the very top of the hierarchy of controls.
But let's be real for a second. If I am a safety professional and I look at an architect's multi-million-dollar design and say, hey, you need to lower this entire pipe rack by 13 inches to protect the worker's rotator cuffs, the project manager is going to laugh me out of the room because that costs money.
Yeah, absolutely will.
Right, unless, of course, I have serious institutional backing. Which brings us to the foundation of any ergonomics program. Management commitment.
Without management commitment, your ergonomics program is dead on arrival.
Yeah.
Full stop. And for the ASP exam, you need to know what constitutes actual commitment.
It can't just be a poster in the break room.
No, it cannot be a vague, nice-sounding policy statement framed in the lobby. It must be demonstrated in deeds and dollars.
Putting their money where their mouth is. They have to actually fund the engineering changes. But from a regulatory standpoint, how is this enforced? Because OSHA doesn't actually have a broad general industry ergonomics standard, do they? They repealed it back in the early 2000s.
That is a crucial point for the exam. You're correct. There is no specific OSHA ergonomics standard for general industry like there is for, say, fall protection or lockout tagout.
Okay.
However, OSHA actively cites ergonomic hazards under the General Duty Clause, Section 5A1 of the OSH Act, which requires employers to provide a workplace free from recognized hazards that are causing or are likely to cause death or serious physical harm.
So if an employer has a high rate of back injuries and they are doing nothing to fix the lifting process, OSHA can hit them with a general duty violation.
Absolutely. And to defend against that, companies often try to implement written ergonomics programs. But here's the trap. You cannot just buy a generic prepackaged ergonomics manual off the internet, slap your corporate logo on it, and put it on a shelf.
A paper program.
Exactly. A paper program is a massive liability. If an OSHA compliance officer walks in due to complaint, they don't just read your binder, they go to the floor.
Right, they want to see it in action.
If your generic manual says employees must use vacuum hoists for loads over 50 pounds, but procurement never allocated the dollars to buy those hoists, you have just provided the inspector with documented proof that you are ignoring your own recognized safety protocols.
Oh, wow. So you practically wrote them the citation yourself.
Yes. The citation will be willful, and it will be astronomically expensive. The written program must be intricately tailored to the specific operations and unique hazards of that specific organization.
That economic reality, the OSHA fines, sure, but also the workers' compensation claims, the lost productivity, the medical costs of a single surgical spinal infusion, that economic reality is what you use to get management to write the checks.
Exactly. Speak their language.
So let's assume you've made the business case. Management is fully on board. The next step in program management is establishing an ergonomics team. Who exactly needs to be on this team?
A successful ergonomics team must be multidisciplinary. You need safety and health personnel, obviously. You need engineering or maintenance staff who actually know how to modify equipment. But crucially, you absolutely must have supervisors and trained floor workers.
Why the floor workers? Some managers might argue they don't have the engineering background to design workstations.
Because the engineers don't do the job 8 hours a day. The floor workers are the experts in the microfrictions of the task.
That makes total sense.
They know that a specific pneumatic tool vibrates strangely after an hour of use, or that the packaging on a certain part requires an awkward pinch grip to open. If you don't include them, you engineer solutions for problems that don't exist, and you miss the hazards that are actively causing harm.
So the team needs the authority to integrate the human factor into purchasing decisions and production planning. Okay, so the team is assembled, we have our budget, now we have to figure out where the actual hazards are. We need to conduct a worksite analysis. But earlier we talked about the invisible nature of these injuries. How do you analyze a hazard that doesn't explode or leak?
Worksite analysis for ergonomics is a systematic data collection process. You start by looking at the lagging indicators.
So looking backward.
Right. You review the existing records, the OSHA 300 logs, workers' compensation claims, and first aid logs. But you aren't just counting numbers. You are looking for insidious, slow onset trends.
So I'm looking for like a cluster of sprain and strain reports on the second shift packaging line, for example.
Exactly. But looking at injuries that have already happened is still reactive. To be proactive, you utilize health surveillance. This is the systematic collection of worker data to spot illness trends or adverse workplace exposures before they turn into recordable injuries.
What does that look like in practice? Are we giving them medical exams every week?
Not necessarily full exams, but symptom surveys and active reporting channels. If you have a system where employees feel comfortable reporting, hey, my wrist is experiencing a lot of fatigue and tingling by Thursday afternoon, that is surveillance data.
Oh, I see.
It prompts an immediate job and task analysis. You go to that specific operation, you establish a baseline, and you break the job down into its individual biomechanical steps to identify the precise risk factors.
Let's dive deep into those risk factors. For the ASP exam, you can't just say it looks dangerous. You have to use the specific taxonomy of ergonomic risk.
You really do.
The outline highlights repetition, force, awkward or static postures, and environmental stressors. We need to understand not just what these are, but how they mechanically destroy human tissue. Let's start with force. We aren't going to define force as just pushing hard. How does an ergonomist actually quantify and analyze force?
Force is the mechanical effort required to perform a task. We quantify it using tools like dynamometers to measure grip strength or push-pull scales to measure the exact poundage required to move a cart. High force demands put massive shear and compressive stress on joints, ligaments, and muscle fibers. But it's not just lifting heavy boxes. Force is highly dependent on the interface.
Give me an example.
If a worker has to use a pneumatic wrench, but the handle is smooth metal covered in oil, the coefficient of friction is nearly zero.
So their hand wants to slide right off.
Precisely. Because of that low friction, the worker has to exert an immense, sustained isometric pinch force just to keep the tool in their hand, let alone operate it. They might be exerting 40 pounds of grip force to manage a 5-pound tool. That excessive force leads directly to tendinitis.
That is wild. Next is repetition, frequency of motion.
The human body is incredibly resilient, but it requires perfusion blood flow to heal. When a task requires the exact same isolated movement thousands of times a shift, like scanning groceries or driving screws on an assembly line, the muscle fibers and tendons undergo microtrauma. If the repetition is so frequent that there is no recovery time, no time for blood to flush out metabolic waste and bring in repair nutrients, that microtrauma compounds into severe inflammation. That's how a seemingly lightweight task destroys a joint.
Now let's look at awkward and static postures. The difference here is fascinating. An awkward posture is deviation from neutral. Neutral being where your joints are naturally aligned, like standing relaxed with your arms at your sides.
Right. When you deviate from neutral, reaching far overhead, twisting your torso while lifting, or bending your wrists at sharp angles, you severely decrease your mechanical advantage.
Because you're out of alignment.
Exactly. The muscles have to work significantly harder just to hold the joint in that compromised position, and the tendons are often stretched tightly across the underlying bones, creating massive internal friction.
And a static posture, that's when you are holding a position, even a completely neutral one, for a long time without moving. Why is standing completely still dangerous?
It comes back to blood flow. Your muscles act as a secondary pump for your circulatory system. When you move, the contracting and relaxing of the muscles pumps venous blood back to the heart.
Like walking.
Right. When you hold a static posture, like standing lock-kneed at a workbench or holding a heavy tool out in front of you, the muscles are in a state of continuous isometric contraction. They are constantly squeezing the blood vessels shut.
So you are inducing localized ischemia.
Exactly. Blood flow is restricted, oxygen delivery drops to near zero in that tissue, and lactic acid and metabolic waste build up rapidly. This leads to acute fatigue, severe pain, and eventually cellular damage. The human body is designed for dynamic movement, not to act as a load-bearing statue.
Here's where it gets really interesting and honestly a bit counterintuitive. The exam outline lists other environmental stressors, and it includes temperature conditions like cold, alongside vibration and contact stress. Most people wouldn't associate the thermostat setting in a warehouse with an ergonomic hazard.
It is a critical multiplier. Environmental factors rarely act alone. They act as catalysts that severely worsen force, repetition, and posture. Let's build a realistic scenario to explain the exact biological failure points.
Let's do it.
Imagine a worker in a meat processing facility. They are stationed at a conveyor belt, manually cutting and sorting specific cuts of tough meat.
All right, I've got the picture.
Let's stack the deck. First, repetition. They are making the exact same slicing motion with a knife 400 times an hour. Second, force. The meat is tough, the knife edge degrades quickly, requiring significant downward muscular effort. Third, awkward posture. The conveyor belt is slightly too wide, forcing them to lean their torso forward, extending their reach, and deviating their wrist to make the cut.
That alone is a textbook recipe for severe musculoskeletal disorders.
Now turn on the environmental stressor. For food safety, that facility is kept at 36 degrees Fahrenheit. How does that cold air biologically impact the worker's ergonomic risk?
Well, the body preserves core temperature by restricting blood flow to the extremities. Vasoconstriction.
Exactly. The blood vessels in the hands and forearms constrict. As blood flow decreases, the temperature of the synovial fluid inside the joints drops. Synovial fluid is the body's natural lubricant. When it gets cold, its viscosity increases.
It gets thick.
It gets thick and sluggish. The tendons no longer glide smoothly, they drag. Furthermore, the worker loses tactile sensation in their fingers. Because they literally cannot feel the handle of the knife as well, the brain compensates by commanding the hand to grip the knife with 2 to 3 times the necessary force.
Wow. So the cold environment chemically and neurologically forces the worker to violently amplify the force risk factor while simultaneously thickening the joint fluids, making the repetition friction much worse.
Precisely. Now, swap the manual knife for a powered vibrating saw. You introduce vibration. Vibration mechanically damages the endothelial cells, lining the blood vessels in the hands, leading to vasospasms.
Is that what they call white finger?
Yes. Over time, this causes hand-arm vibration syndrome, or HAVS, also known as white finger, where the tissue actually dies from lack of circulation.
And what about contact stress?
Contact stress is localized mechanical pressure. If our worker is resting their forearms against the sharp metal edge of the conveyor belt while they cut, that hard edge physically pinches the ulnar or median nerves and the blood vessels against the bone. It acts like a tourniquet.
It's all just biomechanics and fluid dynamics. All these external inputs, the cold, the vibration, the localized pressure, the repeated motion, they aggressively stack up until the biological system physically breaks down.
Which is why worksite analysis must be entirely comprehensive. You cannot simply tell a worker to be careful. If the environment is systematically destroying their tissue, no amount of carefulness will save them.
Right.
Which leads us to the absolute core of the safety professional's job, taking action. Once you've mapped the hazards, you have to physically rebuild the environment.
This brings us to engineering the workspace, the rules of design. We're moving from pathophysiology to actual measurable physical specifications. Let's talk about work surface heights. If I am setting up an assembly line or a workbench, how high should it be?
The cardinal rule is that work surface height is dictated by the specific task being performed, and the reference point is always the worker's resting elbow height.
So it's not a standard 30-inch desk across the board.
Never. If the task involves fine visual details, like assembling microelectronics, inspecting jewelry, or drafting the work surface must be set above elbow height.
Why? Mechanically, what does raising the desk accomplish?
It brings the visual target closer to the eyes without requiring the worker to compromise their spine. If a precision task is placed too low, the worker is biologically forced to flex their cervical spine, bending their neck, and hunch their thoracic spine forward to see what they are doing.
Like looking down at a smartphone.
Exactly. Holding a human head, which weighs about 10 to 12 pounds, out in front of the body's center of gravity places immense static tension on the neck and upper back muscles. By raising the surface, the spine remains stacked in a neutral, upright position.
But what if the work isn't delicate? What if it requires heavy physical effort, like packing dense boxes or using a manual press tool to snap heavy plastic parts together?
Then the rule flips. For tasks requiring heavy downward force, the work surface must be set significantly below elbow height.
Explain the physics there. Why below the elbow?
Mechanical advantage. If you have to push down with 30 pounds of force, and the desk is at or above your elbows, you have to rely entirely on the isolated strength of your triceps and your delicate rotator cuff muscles to generate that force.
That sounds exhausting.
It is exhausting and highly prone to injury. By dropping the work surface below the elbow, the worker can lock their arms and lean their upper torso over the task. They are now using the mass of their own upper body, aided by gravity, to apply the downward force. You transfer the physical load from the small muscles of the shoulder directly to the skeletal structure and gravity.
You're just letting gravity do the heavy lifting. What about the reach zone, the horizontal distance?
The primary design rule for horizontal reach is that the primary work area, the zone where the most frequent, repetitive, and critical tasks occur, must be designed so that arm extensions of more than 15 inches are strictly minimized.
The 15-inch rule, that is a highly testable number for the ASP.
It is. Remember that number.
I think the best way to visualize this is the crowbar analogy. If you take a crowbar to pry a nail out of a board, the spine is the fulcrum. If you hold a 10-pound tool close to your body, your lower back only has to manage 10 pounds.
Right.
But if you fully extend your arm out 20 inches to operate that tool, you have just created a massive lever. The load hasn't changed, but the mechanical torque applied to your shoulder and lower back multiplies exponentially. The muscles have to fire violently just to keep you from falling forward.
Yeah.
So if you design a workstation that forces a worker to reach beyond 15 inches hundreds of times a shift, you are effectively using a crowbar on their lumbar spine all day long.
That analogy is mathematically accurate. The further the load is from the body's center of gravity, the greater the moment arm and the higher the compressive forces on the L5S1 spinal disc. You must design the workspace so that everything necessary is within an immediate, effortless envelope, exactly like a pilot in the cockpit.
Let's talk about the chair. Seating is the interface between the worker and the environment for up to 10 hours a day. The program requirements for seating are very specific. An adjustable height is obvious, so we can match the worker to the required elbow height surface.
Of course.
An adjustable backrest with lumbar support is obvious to maintain the natural lordotic curve of the lower spine. But the outline has a highly specific rule regarding the padding.
Yes. For industrial and proper ergonomic seating, the padding on the seat pan must not compress more than 1 inch under the seated individual's weight.
Wait, I have to push back on this. If you walk into any modern corporate office, the entire high-end ergonomic chair industry is dominated by thick, contoured memory foam or suspension mesh that sinks deeply. People pay $1,000 for a chair that feels like a plush cloud. Is this 1-inch compression rule actually scientifically sound, or is it an outdated industrial standard from the 1980s?
It is deeply scientific, and it explains why those plush executive chairs often cause chronic lower back pain. A chair that feels amazing for 5 minutes in a showroom is often a biomechanical disaster over an 8-hour shift.
Okay, lay out the physiology for me.
When seat padding compresses deeply, the worker's pelvis sinks down into a pit. Consequently, the front edge of the seat pan curves upward relative to the pelvis. That hard upward edge presses directly into the gluteal region, the underside of the thighs behind the knees.
Which is exactly where the major blood vessels and nerves run down into the lower legs.
Precisely. A deeply compressing seat acts as a gentle tourniquet, restricting venous return from the legs, leading to swelling, deep vein thrombosis risks, and nerve numbness.
Thanks.
Furthermore, a highly compressible surface does not provide stable skeletal support for the ischial tuberosities, or sit bones. Because the foam collapses unevenly, the pelvis inevitably rolls backward into a posterior pelvic tilt. When the pelvis rolls back, the natural inward lumbar curve of the spine flattens out, and the anterior portions of the spinal discs are crushed together under the weight of the upper body.
So the soft chair actually forces your spine out of alignment and pinches your disc.
Yes, the 1-inch compression limit ensures that the seat distributes weight evenly across the sit bones to prevent pressure sores, while maintaining absolute structural support so the pelvis stays locked in a neutral upright position. The comfort should come from proper skeletal alignment, not from sinking into a marshmallow.
That is a phenomenal insight. Before we move on from design, what about the cognitive interface? Displays, monitors, control panels?
This is cognitive ergonomics. The principle is based on minimizing mental processing time and error rates. Displays and dials must be simple, logical, and mapped intuitively to human expectations.
Give me an example of an intuitive mapping.
If a dial controls pressure, turning it clockwise should increase the pressure, and the gauge should move to the right or upward. If the interface violates these deep-seated psychological expectations under stress, the worker will make a critical error. The interface must minimize cognitive load.
So we have built the perfect desk, chosen the structurally sound chair, and optimized the control panel. But a massive portion of occupational work isn't sitting at a desk. It's moving heavy physical matter through space.
The real heavy lifting.
Right. Which brings us to mastering manual material handling controls. This is the domain of catastrophic lower back injuries. When a safety professional tackles manual material handling, where do they start?
We always start with the foundational framework of safety, the hierarchy of controls. This is a systematic step-by-step approach to mitigate risks to a level that is as low as reasonably practicable.
Okay.
The hierarchy, from most effective to least, is elimination, substitution, engineering controls, administrative controls, and PPE.
So for a process that involves lifting heavy steel parts, the very first question isn't, how do we teach them to lift better? The first question is elimination. Can we automate this process with a robotic arm so a human never even touches the part?
Exactly. If we cannot eliminate the manual lift, we move down the hierarchy to specific engineering and administrative handling controls. The first tactical approach is simply reducing the size or weight of the objects being lifted.
That sounds almost too simple.
It is simple, but it requires that multidisciplinary team we built earlier. A safety manager can't unilaterally change a supplier's packaging. But if the ergonomics team includes the procurement manager, they can dictate that cement powder, for example, must be ordered in 50-pound bags instead of 100-pound sacks.
Oh, I see.
That single administrative supply chain decision mathematically halves the compressive force on the spine of every worker in the receiving bay.
If we can't change the weight, we look at changing the height of the lift.
Correct. The most dangerous segment of any lift is pulling a heavy load directly off the floor because it forces the worker into maximum spinal flexion and maximum knee flexion while fighting gravity from the lowest possible biomechanical disadvantage.
So picking something up from your toes is the worst case scenario.
The absolute worst. If we engineer the workspace by installing waist-high storage racks or scissor lift tables, we change the vertical height of the origin point. The worker can simply slide the 50-pound box laterally against their body, completely eliminating the vertical lifting phase.
Let's go back to our crowbar analogy and talk about the object itself. The exam outline specifically mentions reducing hand distance. How do we change the physical object to pull it closer to the body?
This is where we analyze the horizontal multiplier in lifting equations like the Ajos lifting equation. The horizontal distance from the spine to the center of gravity of load is the single most critical variable in lower back stress.
Okay, so how do we reduce it?
We reduce that distance by removing bulky outer packaging so the dense core of the object can sit flush against the worker's stomach. Or, most importantly, we provide specific cutout grips or handles on the object.
You know, most people assume a handle on a box is just there to prevent you from dropping it on your foot. It's just for grip security.
Grip security, what the NIOH equation calls coupling, is important, but it's secondary. The true ergonomic function of a handle is that it physically alters the geometry of the lift.
Really? How so?
If a heavy box has no handles, the worker has to reach their arms completely around the outside dimensions of the box to squeeze it, forcing the center of gravity further away from their chest. If you cut handles into the sides, the worker's hands can penetrate the plane of the box, allowing them to pull the mast significantly closer to their own center of gravity, drastically reducing the moment arm and saving the lumbar discs.
If we connect this to the bigger picture, it's just brilliant engineering. What about moving objects across the floor? We have the eternal debate, push versus pull and lift versus carry.
The biomechanical rule is absolute. You must convert load lifting, carrying, and lowering movements into a push or a pull whenever possible by using engineering controls.
Why is carrying so much worse than pushing?
When you carry a heavy load, your spine is bearing 100% of the vertical gravitational force of the object, plus your own upper body weight. Furthermore, walking while carrying introduces dynamic asymmetric shock loading to the spinal disc with every step you take.
And pushing.
When you put that load on a cart and push it, the cart and the floor bear 100% of the vertical gravitational load. The worker only has to exert enough lateral force to overcome the rolling friction of the wheels. You reduce a 200-pound vertical load into a 15-pound horizontal force.
And between pushing and pulling a cart?
Pushing is vastly superior. When you push, you can lean your body weight into the load, utilizing the massive muscle groups of the legs and the core while maintaining a neutral, forward-facing spine. You also have an unobstructed view of your path of travel.
Okay, and why is pulling bad?
When you pull a heavy cart, your arm is often extended behind you, putting the shoulder joint in a vulnerable, biomechanically weak position of extension. Worse, pulling often forces the worker to twist their lumbar spine, to look over their shoulder to see where they are walking.
Which is terrible for the discs.
Twisting the spine while under load is the most efficient way to rupture an intervertebral disc. And if the cart gains momentum, it will run directly over the worker's heels.
So we convert everything to pushing using engineering controls. The outline lists conveyors, hand trucks, four-wheel carts, and ball caster tables. Let's look at the ball caster table because it perfectly illustrates these physics. A worker is at a station where they need to take heavy, flat metal plates from one machine, turn them 90 degrees, and feed them into another machine. If they do that by hand, they are lifting vertically, twisting their spine, and lowering over and over.
Right, a terrible movement pattern.
But if you install a ball caster table, a surface covered in omnidirectional steel roller balls between the machines, you completely alter the kinetic chain.
Exactly. The ball caster table zeroes out the vertical gravitational force. The table bears the entire weight of the steel plate. The worker's spine is completely removed from the compressive equation. Now, the only force required is overcoming the minimal static friction of the steel balls to slide the plate laterally. A task that was slowly destroying the L5S1 disc is converted into a virtually effortless flick of the arms. That is the essence of proactive ergonomic engineering.
It is brilliant. It is just applied physics using mechanical advantage to protect the biological machine. But there is one massive, unpredictable variable in this entire system that isn't purely mathematical, and that is the human being operating within the system. You can engineer the perfect ball caster table and buy the perfect 1-inch compression chair, but if the human decides not to use them or doesn't know how, the entire system collapses.
It completely fails.
Which brings us to the final critical pillar, the human element, worker involvement, training, and evaluation.
This is exactly where the majority of well-funded, technically sound ergonomics programs fall apart. They focus entirely on the engineering blueprints and completely ignore the end user. The workers are the essential element to the program's success. As we established when building the ergonomics team, workers must be intimately consulted for input on risk factors and workstation evaluations.
Because if an ergonomist flies in, observes a line for 20 minutes, installs a new automated lifting arm without talking to the operator, and flies out, the operator is almost certainly going to bypass the control.
They will push it out of the way on day one. If the automated arm is slightly slower than doing it by hand, and the worker is under pressure to meet a production quota, they will bypass the safety device to hit their numbers.
So the worker needs to understand the why.
Buy-in is everything. If the ergonomist didn't consult the worker, they wouldn't understand that friction point. If the workers do not fundamentally believe the engineering changes are designed to protect their livelihood and reduce their pain, they will resist the change.
But this involvement isn't just about making the workers feel heard. It's a two-way street. The outline clearly specifies worker responsibilities. The company isn't solely responsible for everything, right?
An ergonomics program is a legal and ethical partnership. The employer's absolute duty is to provide a workplace free of recognized hazards, to purchase the proper tools, and to design safe workflows. However, the worker has a strict responsibility to use those tools correctly.
Right.
If the company spends $15,000 on a pneumatic vacuum hoist to lift heavy barrels and trains the worker on it, but the worker decides it's faster to just heave the 80-pound barrel by hand, the worker is actively violating the safety protocol. Workers have a responsibility to not bypass administrative controls, to report deteriorating conditions like a cart with a broken wheel that requires massive force to push, and to actively apply the knowledge they gain from training.
Speaking of training, what is the actual standard here? Because I've sat through safety orientations where the ergonomics training was just a grainy 5-minute VHS tape from 1995 telling everyone to lift with your legs, not your back. That can't be sufficient for a modern program.
It is wildly insufficient. And quite frankly, the lift with your legs mantra is an outdated oversimplification that often leads to different injuries like blown out knees if the load cannot sit between the knees during a deep squat.
Oh, I never thought of that.
Modern ergonomic education and training must be comprehensive, and it must be provided not just to the floor workers, but to managers and supervisors as well. Everyone must speak the same language of risk.
What specifically must the curriculum cover?
The training must cover the specific safe work practices for their exact job. It must teach them how to properly operate and adjust the engineering controls provided. For instance, if you buy that expensive, highly adjustable chair, you must train the worker on what every single lever does and how to calibrate it to their specific anthropometric dimensions. An adjustable chair is useless if the worker doesn't know how to unlock the lumbar support.
And what about identifying the injuries themselves?
That is perhaps the most crucial element. Training must explicitly teach workers how to identify the early signs and symptoms of musculoskeletal disorders. They need to know that waking up with numbness and tingling in their thumb and index finger is not just getting older, it is the early neurological warning sign of median nerve compression carpal tunnel syndrome.
Because you want them reporting that tingling to the health surveillance system immediately, while it can still be fixed by adjusting their workstation rather than waiting 6 months until they drop a tool because their grip failed and they require surgery.
Exactly. Early reporting is the lifeblood of proactive ergonomics and a key testable point for the ASP exam. This training cannot be static. It must be actively updated as workplace changes occur. If the company installs a new robotic assembly line, the ergonomic risk profile of the operators changes entirely. The training must be updated to address the new specific tasks.
However, we have to state a fundamental, unyielding principle of safety hierarchy here. Training is an administrative control. It relies on human behavior. Therefore, training alone is never a substitute for engineering controls.
Never. You cannot train away a physiological impossibility. If a job inherently requires a worker to manually lift a 150-pound engine block off the floor, no amount of classroom training on proper lifting technique or core bracing is going to make that task safe.
The forces are just too high.
The compressive forces on the spine exceed the biological failure limit of human bone and cartilage. The hazard is simply too great. Training is the glue that binds the system together, but engineering the hazard out is the concrete foundation. You engineer the hazard out as much as mechanically possible, and only then do you train the worker on how to safely interact with the newly designed system.
Okay, so let's put it all together. We secured the deeds and dollars from management. We built a team with the floor workers. We analyzed the OSHA 300 logs and measured the pinch force of the tools. We redesigned the desks to elbow height and bought the 1-inch compression chairs. We replaced carrying with pushing. And we trained everyone on the symptoms of MSDs. How do we know if any of this actually worked?
That is the final required element of the program: tracking and evaluation. An ergonomics program is not a project with an end date. It is a continuous, closed-loop system of continuous improvement.
So you're never really done.
Never. You implement the engineering solutions, and then you monitor them. You go back to the worker 2 weeks later and ask, is that ball caster table actually reducing the strain in your lower back, or is it getting jammed? You adjust the controls based on that feedback.
You are constantly validating your hypothesis against reality. But how do you prove the value of the program to the management team that wrote the checks? What is the ultimate metric of success? It's not having the thickest written manual in a binder, right?
Management doesn't care about the binder. The ultimate metric of an ergonomics program's success is the measurable reduction or prevention of ergonomically related diseases and injuries.
The bottom line.
Right. You track the lagging indicators. Are your OSHA recordable rates for sprains and strains going down year over year? Are the workers' compensation premiums decreasing? But you also track the leading indicators. Are employees reporting less localized fatigue, in the health surveillance surveys? Is the throughput of the line increasing because workers aren't taking micro breaks to stretch out cramping hands?
It's quantifiable human preservation.
Exactly. When you can present a chart showing a 40% reduction in lower back injury claims, perfectly correlated with the installation of waist-high material racks and a robust symptom reporting training program, you have proven the return on investment. You have justified the deeds in dollars, and you have fulfilled your core duty as a safety professional.
So what does this all mean for you, the listener preparing for this exam? It means that understanding an ergonomics program is not about memorizing a list of office furniture. It is about understanding the profound mechanical and physiological relationship between a human being and their physical environment.
That's beautifully said.
The best lifting aids and the most perfectly calibrated work surfaces are utterly useless if the management doesn't fund them, if the worksite analysis doesn't properly diagnose the hazard, and if the culture doesn't empower workers to be active participants in their own bodily preservation. The science of work only succeeds when the biological realities of the human are placed at the absolute center of the equation.
That is the perfect synthesis. The human factor is the most complex, unpredictable, but ultimately the most important variable in any industrial system.
We have covered a massive amount of incredibly technical ground today. Let's briefly trace the through line of what you need to know for the ASP. We started with the foundational philosophy, the IEA's definition of a systems-oriented discipline that adapts the job to the fixed limitations of the person.
And we detailed the absolute necessity of management's financial and authoritative commitment to avoid the lethal trap of paper programs.
Right. We broke down the mechanics of worksite analysis, moving from reactive OSHA logs to proactive symptom surveillance.
We then explored the pathophysiology of the core risk factors, how force, repetition, static postures, and environmental catalysts like cold and vibration mechanically degrade human tissue.
And we translated that pathology into physical design rules, setting elbow heights based on physical versus visual demands, maintaining the 15-inch reach envelope to neutralize spinal leverage, and the biomechanical necessity of the 1-inch chair padding limit to protect pelvic alignment.
From there, we tackled manual material handling, applying the hierarchy of controls to eliminate vertical lifting, using handles to bring the center of gravity closer to the spine, and utilizing equipment like bulk caster tables to convert devastating compressive loads into manageable lateral pushes.
And finally, we locked it all together with the human element, the absolute necessity of worker involvement, targeted training that goes beyond outdated cliches, and evaluating the program's success through the actual reduction of human injury. This has been a granular, tactical exploration of the elements of an ergonomics program.
It really has. And before we conclude, I want to leave our future safety professionals with a thought to mull over as they enter the field.
Go for it.
We have spent this entire time discussing the physical loads of the modern industrial world. But as our workplaces become increasingly automated, as artificial intelligence and robotics take over the heavy manual material handling, how will the science of work evolve? Will the proactive ergonomist of the next decade be less concerned with the physical weight of a wooden pallet and more concerned with the immense cognitive load and psychological stress of augmented reality interfaces and hyper-monitored remote work?
That is a profound question. The nature of the hazards will shift from the musculoskeletal to the neurological.
Precisely. But as you move forward in your safety career, remember the one constant. The biological limits of the human body and the human mind remain the exact same, even as the nature of the tools and the work drastically changes.
The human remains the center of the system. Thank you for joining this edition of QHSE Talks. We know how rigorous the ASP exam is, but mastering these mechanisms won't just help you pass, it will make you an elite protector of human life in the field. Keep studying the mechanisms, keep questioning the physical reality of the tasks you observe, and remember to always keep adapting the world to the worker. We will see you next time.